welcome back. And I had a question from the previous videos about designing servos around motors like this, motors and encoders. There's an encoder at the other end, as to how to identify the transfer function of these motors. And that's a question that would be very easily answered in the older days, because what we used to do there is we just put a sine wave into it and do a frequency response test, and that was very time consuming, but you need a power amplifier basically, and you put a sine wave in from an oscillator and you measure on the oscilloscope the amplitude of the output and the input and divide the two and you get a Bode-plot. Now we've kind of moved on to the digital world where we've got microcontrollers and we don't even have DC amplifiers anymore. We've got H-bridges like this, and I suppose the question arises, how do we do this in the modern world? And although we probably can still do the frequency response, I've been testing out this, not a new method by any means, but the method of recursive-least-squares, which I remember using in my PhD at least, I don't know how many years ago, 30, 40 years ago. Recursive-least-squares, I thought at the time, was a relatively new thing, but of course it turns out to be that Gauss himself discovered this in 1820, but he kind of dismissed it because he had ordinary least squares, and he probably thought, what's the point in having recursive least squares? We don't really need it. There was no computers at the time. So what recursive least squares is it's a way of fitting a model, if you like, to data of the input and the output, and it does it step by step. So this is of course ideal for a microprocessor where you're sampling, and every new step you get a kind of better estimate. The problem with recursive least squares has always been that it's kind of computationally a bit tricky. And nowadays not such a big problem, but if we try and implement it in real time, and they're often used for adaptive filters in this kind of application, then it can actually turn out to be quite a burden on the processor. So because of that, because lots of people do simulations with recursive least squares. So because of that, I'm not going to use it in real time. I'm going to sort of run it offline because I don't really need real-time results. All I need to do is to gather the data and then fire it through my algorithm. And what the algorithm is, here's the algorithm, if you can see it here. It's you can have a pole zero model or a all zero model or an all pole model. You can really do it any way you like. Here's an example here of a second order, a third order with a first order numerator, and we could estimate these parameters B0, B1, A1, A2, A3. This is what you'll see in all the textbooks. And you can write it like this. It's often called an autoregressive moving average model, ARMA, in statistics. And you can write it in vector form, with theta as the parameter vector, the unknown parameter vector, and x is this vector of regressors, of past values. And we assume that the weights are, we call these weights or parameters, are constant and they don't change with time. Of course, in adaptive filtering we would expect things to change with time, and therefore they would need to be done online in real time. But because our motor characteristics isn't going to be changing, or if it does change, it's very, very slow in sort of terms of years maybe of things do change with wear, then we don't need that. So we can just take the data and then fire it through the algorithm. If it was time varying, we could sort of model it as theta k is theta k minus 1 plus a noise term, and in order to estimate that unknown vector, then we'd use a Kalman filter. Of course, the Kalman filter only came out in the 1960s, whereas recursive least squares have been around since 1820, although we were using it quite frequently in the 1970s. A lot of adaptive control, self-tuning control and so on. It was nearly all simulations in those days. This is the algorithm. You just update the parameter vector. Theta k plus 1 is theta k, and this bit here is a kind like a Kalman gain vector, px over 1 plus x transpose px, and that's an error. In fact, recursive-least-squares is a feedback system that's time varying in itself, which is quite interesting. That's another matter. And then we update this p thing, which is called the error covariance matrix, exactly the same as in the Kalman filter. And the only difference is we don't know what any noise variances are. We assume we don't know any of that, and that everything's so-called deterministic. There's no noise around, so it's called deterministic least squares. If you had the noisy version, it would have to be the Kalman filter, and you can do that with a Kalman filter as well. So we could do the same thing, but we'd have to know how the statistics of the parameters change with time, and we don't have that problem here with a motor. So this is the error covariance matrix. We normally start it off as a diagonal matrix. You know, give it some values, 10, 100, whatever. If you make it very, very small values that you start it with, then it converges a bit slower than large values, and you get faster convergence. So that is the recursive-least-square. So how do we go about implementing this in our system? Well, I've written a program, if I can find it. Here it is. So I've written a program, and what it does is it reads the data. Now, what data? Well, the data is what I have to do is I have to get the motor running, which I do, and I add in white noise into it. The thing about recursive-least-squares is it doesn't work if you just put constant values in. It needs what's called persistently exciting signals. There might not be anything exciting to you about a signal, of course, but persistently excitation means some sort of randomness in changing signals. So you could put a square wave in, for example, because it's rich in harmonics, but I'm just using white noise, and that's one of the advantages of the digital age. Of course, it's easy to get noise. We can just generate any variance we like. So I superimpose the noise on top of just a DC value of speed, so that the speed's turning round. Then I measure the speed at the output. So I've got data at the input and the output. Most of that's done with the FPGA. I'm just at the upper level here. It's just sort of gathering the data, and it goes through a real-time loop sampled at 10 kilohertz, and then the loop only runs for a few seconds and stops, and outside the loop is the recursive-least-squares. And here's the recursive-least-squares algorithm. It's over here. I wrote this a long time ago, but LabView's also got its own one in a sort of toolkit, but this is my one, doing all the things that in the equations. It's a for loop that goes round whatever many times. This is the regression vector that sort of shuffles the regression vector. These are matrix multiplications and matrix times vectors and so on and so forth. So once we've got the recursive-least-squares, the recursive-least-squares will give us a digital model, a Z-transform model, and from there we can plot the Bode-plot. I suppose you could take the Z-transform model and use some other kind of modeling to go to Laplace and get a Laplace model that way, but as engineers it's probably just as easy to look at the Bode-plot, and then we can get it from the Bode-plot quite easily. And this is using this. So I'm using this little routine here to give some credit to this guy Mark Yoder, who wrote this nice little Bode-plot thing which scans through the frequencies. So given a model, Z-transform model, what this does is it plots the Bode-plot, the analog Bode-plot. We don't really need the phase because it's going to be non-minimum phase, so we can deduce the phase from the magnitude anyway, so that's not really of importance. So here I've got a couple of cursors, so I don't know, we've seen them before, but the nice thing about LabView is we can have these things for measurement, so we can create as many cursors as we like. I've also got a pole zero plot where I can plot the poles and zeros of the digital system. So let's run it. It'll only take a few seconds. I've got to turn it on. I think that might not be a bad idea. So it's running at the moment, but I haven't run the program. And it's doing one of these annoying things where it's saying there's a program already running. So because of that, I always just normally just sort of reinitialize the LabView program when it does that. It's a bit of a nuisance, so it'll pop up again in a second. Where is it? There it is. So that's my myRio. So just saying it's. And now I'll run it. And that should give me. Now that's me into LabView. LabView myRio. And then there should be a file. Oh, there it is, right. The Project Explorer. And then run it. We're back into the program. Now it should run this time. It's deploying. There we go. Right, that's the motor started. And it should run for a few seconds, stop, and plot the Bode-plot. Oh, look at that. There we go. Isn't that remarkable, really? Now, I've cheated a little bit here in that I've already sort of pre-scaled it so that the DC gain's down at unity or 0 dB. I should get the other cursor. One of the annoying things here is that, yeah, the cursor disappears sometimes. So this is my Bode-plot. So you can see, have a look at the slope here. That should be about minus 20 dB per decade, something like that. We can measure anywhere. We can take, what do we take? About there, that's 5 dB to 25 dB or something in a decade. Or we can take it in an octave, which might be easier, because it's not right on the grids there. It's a bit harder to find. So in an octave, which is a doubling in frequency, let's go there, 50 Hertz. So to 100 Hertz is here. That's 100 Hertz where this one is. So we're going from here to here, 100 Hertz. Should go down 6 dB. So it does it. At that point it is minus 21. I might say minus 22 dB, minus 21.9, and down here it should be twice. It's minus 27.7. So 21 plus 6 is 22 plus 6 is 28. Yeah, so it's minus 27.7, almost 28. So it's going down 6 dB in an octave. That octave is a doubling in frequency from 50 Hertz to 100 Hertz, or you could measure it. So this is a straight line, so clearly this is minus 6 dB per octave, or minus 20 dB per decade. If you take the time, you'll find it's minus 20 dB per decade. Whereas the time constant, we need to go down 3 dB from here, so it's 0 dB. That's about 0, showing minus 0.2. We go down 3 dB, minus 2.5, minus 3 dB, so that's gone down minus 3 dB. I'll go along in frequency, and where it intersects, that is showing 4.4 Hertz. So the fast breakpoint frequency is at about 4.4 Hertz. The interesting thing is that you can't seem to see any effectively inductance at all. It's just got the one pole all the way down to about 500 Hertz. There's not much really happening. It's just, so it's going to be K over 1 plus ST. But the beauty is that you see the structural resonance. It comes out really nicely here. Structural resonance at 1.5 kilohertz. And I'm using quite a high order model here, 8th order, all pole. sometimes when you do, you don't seem to get quite the same results every time, but you get close to the same results every time. So I'm run it a second time. There we go. Oh, see, it's not much different, but this time it seems to have picked up a second resonance, and then that makes sense because there's always more than one structural resonance. So it's picked the first one up on the second one. And this is the thing that gives you trouble, this resonance, when you try and operate at a very high bandwidth. If you're running at very low bandwidth, you never see this at all. I mean, it's a lot of control systems and textbooks, they never even mention it because they're just doing very simple things really and running at a few hertz bandwidth, and it's not really what you want to do. You want to try and make the thing respond very quickly. So we can see that this would limit our frequency response. So it's 1.2 I've got this time, 1.5 I had the last time. So it's in that region anyway, after a kilohertz. And so what I'd want to do is I'd want to make the bandwidth of this loop at least 1/10 of that. So 1/10 of 1.2, or let's say 1 kilohertz is going to be 1/10 of that is 100 hertz. So I would think I'd be wanting to make the unity gain here somewhere at 100 hertz. Okay, and you can still see that looks pretty dangerous because that's going to poke up through 0 dB. So I've got to be careful how many phase advances I put in, because I'm going to get an oscillation at that frequency. And even if we did something about that, we could try notching it out or something. You've got other ones coming in. I'll just run it one more time to see what we get. Go again. I got much the same again. Got the two resonances. We've got a pole zero plot here in the Z domain. If we were to take a second order transfer function, we wouldn't get these resonances. So that's why I've picked a high order, because we can basically. And so in the past you could still pick this up with an oscillator. I've seen colleagues doing this. Actually, Pettigrew, my old colleague, used to sit at the oscilloscope and he'd put sine waves in and the motor would start squealing. You can actually hear it whining up at 1 kilohertz. Okay, so that's one way of this. Now I can't see the inductive reactance, so it tells us one thing: it's probably very small compared with the other time constants in there, or it's being swamped by the resistance or something. That's quite interesting, and in this case anyway we're not seeing any evidence of that. But an interesting application, as I say, you see plenty of papers on recursive least squares, and they're going back a long time, but not many of them are actually doing the real thing, using to get real models. They tend to be simulations. I think they take a transfer function and say, look, I can estimate that transfer function. Well, yeah, sure, we can all do that, but getting the real thing is slightly more difficult. So what you have to watch here, there's the parameters converging, is that you operate sort of in a linear region. You don't want to be saturating the motor in any way, so you sort of want to give it running at some reasonable speed well before its limits, and then superimpose a noise term on top of it.